All right, future civil engineers. Hopefully you are enjoying the bridge challenge. And just for inspiration, put together a little PowerPoint for you to inspire you with all these beautiful bridges that we have in our world and all the different designs that go into them that basically have to hold up the load of the cars that are passing through, and of course the materials, right? So this is our load deck right here, where we have all these cars coming through and we need to support all of that in some way. So there's various ways that we can design bridges. Of course, whoops, all bridges, right, serve the purpose. I think we've discussed this before, for walkways, crossing across roads, wellways, pipelines, connecting lands, crossing over rivers and canyons. So no matter what the bridge is like, it's to get you to someplace. It's to allow you to get to another area, right? So whether you're crossing over a river or canyon and so on. So in history, civil engineers have come up with 5 different types. We could categorize all bridges. We have arch bridges, truss bridges, cantilever bridges, cable stayed, and suspension bridges. We're focusing, most of you are using the idea of a truss bridge in this design, in this challenge. What is going on in the bridge? What kind of forces are there? So if you remember way at the beginning of the year, we talked about action and reaction, right? So the idea of a compression force, a pushing between 2 objects on one another, so you're going to compress the material together, is a pushing or squeezing force. Reacting to that often is a tension force, right? So if on one end I'm pushing, I must be pulling or stretching from another area. If we were in class, I would have you guys lean up against one another with your hands, and you would feel that compression. Then I would have you hold hands and put your feet together and lean apart from one another, and you would feel the tension in your arms and in your hands as you try to move in either way. Either way, you're not moving. So one way is both compression would keep you there and the tension would keep it there. It's a matter of what can your material withstand more. So are you able to withstand a compression more or a tension more? And that depends on your material. So let's take a look at each one of the bridges, types of bridges, and what's important in them. So in an arch bridge, you have what's called the keystone, the wedge-shaped stone of an arch that locks the parts together. So I know some of you are considering putting this arch on the top of yours, or some of you maybe on the bottom of your road. So keeping in mind, a lot of the stress is going to come in play right here in the middle, right? So it's going to come into play right here. So instead of that cracking right at the end, if you make a separate piece in which then those pieces are pushing on, right? So take a look at the forces that are going to act on this. Okay. To keep it in place, you're going to want to secure the ends with what's called an abutment, the structure that support the ends of the bridge at the end. And taking a look at the forces that acts on this type of an arch is more of a compression, right? So if this is underneath your road, and you can imagine whether it's underneath or on top, no matter what on the bridge, you're pulling down on it from the weight of all the cars, right? So as that compression force goes down, wouldn't really even be called a compression force, but it would be an external force of all the weight of the cars going down. You'll have a compression at the top at that keystone part. The abutments on the side, of course, it's going, when you push down, it's going to want to spread the legs out apart at the bottom. So you're going to have compression of the arch against those abutments. Notice all the 2 forces, the idea of action and reaction everywhere. So some beautiful bridges that have been designed. Santa Barbara, California, the Cold Spring Arch Bridge. Marsh Rainbow Arch in Riverton, Kansas. And I recently went to the New River Gorge Bridge. If you've ever seen that, that's a beautiful arch bridge. Second, we have a cable stayed bridge, right? A little bit different. You're going to form these piers. So of course, that's going to be driven into the ground, right? And that's just your vertical support, just like that. You're going to hang things from that, your cables. Okay, so of course, you're relying on the strength of the cables to make sure that they can withstand the tension that you're going to put onto these cables. Because as you bring in the decking, you need to be able to support them from the piers. So of course, this is very important to be balanced on both sides so you don't cause any torques taking place and taking all the tension and compression. As the weight of the road acts down, right? Notice the compression within the piers, compression on the decking, but you're going to have tension within the cables, right? So there's going to be tension coming in within the cables. So your initial thought here might be that you would have expected these cables to pull down, but if the cable's pulling down, right, that's actually not going to be the case, because this is going to want to wrap in this way, which is going to cause that compression happening in here. So that's going to pull in this direction. And as that pulls on the cable on the pier is to pull that way. But within the cable, the action and reaction within the cable is you have this tension force. So often what happens to cable always is under tension, right? Or otherwise there, it's a string, it's pliable. So it's not really ever going to be under compression. So all cables are under tension. Just some examples of those. Okay, a suspension bridge. Going to pull in your piers, put these abutments on the side, and lay your decking and suspend it in a vertical way from almost like an inverted arch, right? So again, similar force where we go down, you still have compression happening within the piers as all the forces get distributed. If I go back, take a look at how those forces play out. Okay, causes stress within the cables. There you go. Of course, the Golden Gate Bridge, right? New York, if you've been there, we have some beautiful bridges in New York City. Now, the main one is the Truss Bridge. This is what you guys are mostly focusing on. So the truss is made up of what we call truss members that are beams along each side to support the weight of the decking, right? So we haven't even put on the decking yet. So that's keeping those in line, your top bar. And then we want to put in our decking, and we're hoping that that truss is going to be able to support the decking. And that's what we want to make sure everybody's putting some focus on. So the way this works by tension and compression. So again, take a look at how this force acts. So overall, we have the weight of the road and all the cars pulling down, right? And you're basically setting this bridge on top of these abutments on the right and left, right? So as the weight acts down, you see that all the outside members are in compression, right? So each line, each bar is a separate one. So within the length of that bar, all you see is these compressive forces, right? All the members are in compression. So if we take a look at your three-dimensional view of your bridge, all right? So you don't necessarily need a lot at the top because we're not worried about wind bracing. So you can see these little blue lines that are in here, right? That's going to hold it laterally. That'll hold it from all different forces in different directions, okay? These going straight across was probably sufficient for you. and you're just allowing it to, when it's not going to swing left and right. But what you guys all need to concentrate on is this floor beams, what's going on down here. So as you're designing your decking, in which my little piece of wood is going to go in there, and I'm going to slide it all the way in the middle and simply hang my bucket from that. So the questioning is, how are these all connected at each one of these points? And what is the purpose of this upper truss area right here? So what are we going to be doing in the upper truss area? Okay, so what we want to concentrate on the forces that are going to be acting on this truss. Those are the different types of trusses. I gave you that in class. Right? Some different pictures. Well, let me go back there. I went pretty quick. All right. That's an example of a railroad crossing using the trusses to go across the water. Okay. So once again, you're familiar with this, a free body diagram, right? So the frames are the structures with at least one multi-force member. So frames are designed to support the loads and are usually stationary, right? We don't want this bridge moving anywhere. So we're going to begin with a free body diagram of all the forces, right? And we want to determine the external forces acting on the frame. All the other forces are internal forces, right? So again, imagine a boundary surface around your entire bridge, right? And then what are the external forces that are coming from the outside? You'll have a force from this, where it's sitting over here. And then, of course, Earth is always pulling on everything. So there's going to be a weight to that bridge. These are going to be up on this direction. Then everything else is considered an internal force, right? Just as we have been using all year long on this whole system, doesn't matter its design, you can look at that as a big solid block. All the forces in the X must add up to be 0. As you can see with the forces that I have there, I have no forces in the X direction. All the forces in the Y direction must add up to be 0, which means the upward force on this side and the upward force on this side must add together to equal W. This next equation is that all the torques must be equal to 0. So if I were to choose a pivot point around any of these 3 points right here, all the torques around those points must be 0. It cannot try to rotate or spin, right? So that's the concept behind how do you figure out how much all of these, even the internal forces are, and are they going to be too much for your material that you are building your bridge out of to be able to withstand? Okay. So maybe when we're done with this, we might be able to set up a lab to just take a look at how much force can balsa wood withstand compression and tension. Okay. So basically, that's what I said. We're going to sum up all the forces. Remember that torques are forces that act at a distance. They're going to cause rotation. So if I say summation of torques, that's really a force times a lever arm. So remember that R is the perpendicular distance to the line of force. Right? So perpendicular distance to the line of force. And again, we have our X and Y summations. Okay, so let's take a look at this. Internal forces are determined by dismembering the frame and creating free body diagrams for each component. So we could break this up into A, B, C, right? C, D, E, B, C, D, each member, right? What we do know is these forces are action or reaction forces. So if I find one of them, I do find the other. And each of these specific points, A is considered a joint. B is a joint, right? And if you look at B, what forces would be acting at B? So the number one thing is we assume all beams are in tension, okay? When we draw a free body diagram, all forces from beams, not external forces, but beams, act in tension, okay? So it's going to be in this, they're always going to be pulling away from your joint. If in your calculations you end up with a negative answer for your force, that means you made the wrong assumption for the direction, and it actually is more of a compressive force. So if I can move this out of the way here a little bit, there we go. All right, let's take a look at each one of these. So already B and D are done for you. You can see their forces. What forces would be present at A? So what I would draw at A, I can get different colors here. It has the force going up, that is this one. That's an external force from this block that is located right there. It then also has each of the members, right? There are two members, one at an angle, one horizontally across, connected at joint A. So each member is going to cause a force, making it tension at that point. So we would have tension within that member. At C, so if I take a look at the joint C right here, right, you're going to have the weight and then each one of the members that are on either side of that. So B was already done for you. C, on C, I change my color again, has weight acting down. That's the 20 pounds, right? And then we were going to have each one of these forces all at different angles, right? D, E. E is going to look similar to A, but almost like a mirror image of it, right? So on E, you're going to have the force due to this block right here, holding it up. So it's basically just, it's a normal force almost. So you have this wanting to push down, and it's an external force pushing up. So we're going to have the force from the external forces, and then all we're looking at here then are these members from each of the beams. That's what we want here on E and this way. So hopefully that makes sense to you. What are all the directions of the forces at each one of the joints? So that's your first step in trying to answer the truss problem of what are the forces, what's the magnitude of the forces that are there. Okay. So okay, labeling these as reaction A, reaction E. So action, reaction. So we're going to call that a reactive force. Now I apologize. These are in pounds and feet. Remember, we were using newtons and meters. So in the English system, torque is the same. It's a force times a lever arm, but in this case, your force is in units of pounds and your distance in units of feet. So they're actually looked at as often as a foot-pound as a unit of torque. How many foot-pounds? So you might be familiar with that with some tools that you might have used, wrenches or things like that. All right, so all the torques can only be caused by external forces. So remember, we're looking at this as a big box, right? So the only torque, as if it's like your meter stick, can be caused not by tensions and compressions within the meter stick, but only external forces. So if I make A my pivot point, right? Remember, any forces going through the pivot point do not cause torque. And it's only external forces that we're going to take a look at here that are going to cause torque. So the force of the 20 pounds and the reaction at A are going to cause torque, right? Those torques might add up to be 0. So if I'd write that out in an equation first, I'd say, okay, summation of torques about A must be equal to 0. So summation of torques about A, clockwise positive, counterclockwise, negative. Scratch that out if I have any eraser here. Okay, so you would have, what torques do you have? The 20 pound, so you'd have the weight times the lever arm of the weight, and that's going to make it want to go in this direction, so that's a positive. This one's going to make it want to go in the counterclockwise direction around A, so that's going to be a negative value plus negative reaction E times R of reaction E. So the weight is the 20. It's a distance. The lever arm is 1 foot. Reaction at E, we don't know, but it's 2 feet away. So your total distance over here to E is 2 feet away. They must add up to be 0. So my only unknown here is reaction E. So solving for reaction E, I get 10 pounds, which should make sense, right? Because if I only have 2 upward forces, I would assume that they would both equally split the downward force of 20 newtons. So that gives me the reaction, excuse me, at E. Due to symmetry, or really due to the summation of forces in the Y equal to 0, you'd have reaction of A plus reaction of E minus that weight acting down equals 0. So reaction of A is equal to W minus reaction of E, or 20 pounds minus 10 pounds. Reaction of A also equals 10 pounds, right? So now we know both of these. So if I just look at E, okay, if I just look at E, keeping in mind this is an equilateral triangle, which means each one of these angles is 60 degrees, right? So that means the only force not acting in an X and Y direction is FED, this one right here. So what I can do with FED, right, is break it up into components, FED in the X direction and FED in the Y direction, so that my real free body diagram will be FEDY, FEDX, FEC, right? And along with that, you'd have FE. So you can already see that's not possible, right? Because I can't have everything going up and everything going to the left. So this is a case where you might end up with a negative answer, which means we assume the wrong direction for this member right here, I'm guessing, right? Because if this is pushing up, something must be pushing down. But remember, we start the problem with the assumption of everything being in tension. Now, if that is 60 degrees, then I would say the cosine of 60 degrees is equal to adjacent FEDX divided by FED. So FED cosine 60 degrees equals FEDX. Sine of 60 degrees equals FEDY divided by FED. So FED sine 60 degrees equals FEDY. All right, hopefully that makes sense. So that's breaking that up into components, right? This is my true free body diagram. I have my components. I know what FE is. It is 10 pounds. Okay. So this is jumping ahead a little bit here. Let me go back to our picture that we had. Let's see if it'll take me back here. It's just getting a little bit messy. All right, so then I'm going to switch to what are the summation of forces here, right? So if I would say, okay, summation of forces in the x equals MAX, which that's going to be 0. Remember, to the right positive, to the left negative. So in the x direction, you have everything in the negative. You have negative FEC minus FEDX equals 0. So FEC equals negative FEDX. FEDX, so, oops, shoot, sorry. FEDX equals what you have down here, FED cosine 60 degrees. So that means that equals FEC, which doesn't seem like it's getting us anywhere, right? So let's see, where do I have the FE, which is in the Y? The Y direction might get us more information. So we're going to pause from this and let's go into the Y. Summation of forces in the Y equals FEDY plus FE, and they must be 0. So FE equals negative FEDY. So FE equals FEDY, remember, was down here. FED sine 60 degrees. So FE divided by, we're going to put the negative over here, sine 60 degrees equals FED. So plugging that in, you get 10 pounds divided by the sine of 60 degrees equals FED. Not enough space here. Need my whiteboard. So 10 pounds divided by the sine of 60 equals FED. Plugging that in your calculator, you get your answer, right? So you can plug that into your calculator, get your answer. So you get FED, right? Remember, we had a negative here. I'm going to write it up here because I don't have much space left. I get FED equals negative 11.547 pounds. Now remember, the negative means it should be acting in the opposite direction. So it should actually be acting to go down. So we need FDY to go down. I switch my colors here. We actually want that to go down. The same thing is true if that's a compressive force, then over here, then that means FDX is going to point that way. So once I know FED, I can use that over here to say that times the cosine of 60 is going to give me FED in the x direction. So FEDX, right? So sloppy, I hate this. Don't like the way I've written this. Equals, right, negative the 11.547 times the cosine 60 degrees. So FEDX, which is what you're looking for in order to get FEC. And if we plug that into our calculator, All right, I'm going to pause here because this is just getting even too sloppy for me, for you guys to look back. So I'm going to end this real quick. See if I can minimize it. I think I have to end it to get to my whiteboard that I want to use instead. Oh. And, all right, let's get to our whiteboard here real quick. All right, so just going back to what we were doing, right? So we have at the joint E, right? We had FE acting up, and then we have this bar coming in here and this bar coming across. This was FEC, and this was FED, correct? So when we take a look at that, just want to make sure that was the case. Go back over here. FED, yep, along here. All right, so just to clean it all up a little bit. So it was FED, right? We want to break up into components to say that it can be broken up into, if this is FED, it's going to have an X component. We call it FEDX, and a Y component, FEDY. So if that's 60 degrees, then what we know is we take the cosine 60 degrees, that's going to be equal to adjacent FEDX divided by FED. Right? All right, I'm going to switch this up so I can write a little bit neater here. Now, when we say sine of 60 degrees, that's going to be the opposite, FEDY divided by FED. So FED sine 60 equals FEDY. FED cosine 60 equals FEX, right? So our true free body diagram, which we now recognize will end up with negative numbers, is we have FEDY, FE, FEDX, and FEC. So if we do summation of forces in the X equal to 0, and summation of forces in the Y equal to 0, what we do know here, right? So remember, list what you know. The one thing we know is FE is equal to 10 pounds. Right? So we do know that information, and we know the angle to be 60 degrees. So in the X direction, X and Y, we just take a look at the X direction. Oh, didn't even realize I'm on a different whiteboard here. All right, we'll try to squeeze this in. So in the X direction, we would have FEC, right? Minus, they're both going in the negative, FEDX equal to 0. So FEC equals FEDX. FEC is equal to FED cosine of 60 degrees. So if I can find FED, so I'm going to go to the Y direction. And in the Y direction, you're going to have FE plus FEDY is equal to 0. That means FEDY equals negative FE. and that's 10 pounds, right? So that equals negative 10 pounds. FEDY, looking up here, plugging that in here, right? We get FED sine of 60 degrees equals negative 10 pounds. So FED is going to be negative 10 pounds divided by sine 60 degrees. So we get FED equal to, plugging that in our calculators. Okay, as we saw, FED equals 11.54 pounds. So we're going to use that. And I apologize. I mistakenly pulled up a whiteboard that I had something else on. So we're going to use that here, right? That means FED equals 11.54. FEC equals 11.547 times the cosine of 60 degrees. So FEC equals, plugging that into your calculator, 5.77 pounds. So plugging that into your calculator. So this here is no different than you've done before on free body diagrams, right? So we had all of these forces acting at that one joint. So we're just looking at one particular point. What we recognize here is that these are in opposite directions. So we assume the wrong direction for FEC. It should actually be pushing this way. It should be putting in that direction on the joint. All right, so it's going to be a compression point to the joint, but it's going to look like that. And within the member, it's going to cause tension within the member, and FEC is going to cause tension within the member. Okay, so these are our values of those. Now we can go back and put that into our it's going to stir me all the way through there. Thought it would take me back to the original. Let's see. I'll just quickly go through them all. All right, so since it was getting so sloppy there, we switched to the whiteboard, right? So hopefully you have all that information. And you're seeing the same thing here, adding up all your forces in the y direction. We had our 10 pounds, solving for that. We got the 11.57. Remember, negative means we assumed the wrong direction. FEC, same thing. We assumed the right direction for that. And so we would go back and change our direction here to be that it's pushing on that. So action and reaction, if this member is pushing down, right, then we have compression within there. These all have to be equal to one another. So then that means this is also equal to the 11.567. Action, reaction, we can keep going around and taking a look, and you'll see that that same force is all the way through because of symmetry. So FED is equal to FAB on this side, right? And then that's going to carry over into your joints there. And then we can just continue on and find the tension and compression in each one of those joints. I'm going to skip through that for now because on your homework, all you're asked to do is find what's going on here. So that's enough information to give you that. And let's see, I'm going to go through that quickly just on these slides. Okay, so if you show the tension and compression, you will find that across the bottom, you have the same amount of forces, and on the top, they are all the same. Around the outside, we have all compression going on, and on the internal members inside, you have all tension taking place. So depending on the forces that that beam can withstand, then that's how I would determine, where I'm going to put, how big the triangles have to be, how much support do I have to have there. Excuse me. Okay, so that's how you do your analysis. If you run verticals here, you will see that we were able to do that. So now that all of those forces are okay, adding in vertical components, we would call those zero force members. So if I put those in there, they may not be necessary. Looks nice, but you'll find that sometimes those members are not necessary. So those were some of the joints. Just wanted to remind you guys of, as you are building these, that it's in here that I'm going to lay that piece of wood. So that member right there has to be able to support the weight pulling down on it. So be careful of what you are designing on your road surface. Okay. So I think that's it. I'm going to, whoops, end the PowerPoint. And hopefully that helps you in the designing of your bridge, and most importantly, in completing the mathematical calculation of what we need to do on your problem. So let's see, I'll keep that for now. Let's go over to this problem, right? So here's your problem that we want to take a look at. Looks very similar, right? Now, what I did not give you here are the angles. So you, given these lengths, okay, the distance is in here. This is a right triangle. I'm going to challenge you guys to figure out what that angle is right here. So I've given you this side and that height. It is not a 60, 60, 60. It is not an equilateral triangle. All right. So you don't have to solve for other values besides what's going on at D. So my question is, calculate the forces at joint D only. Okay. So good luck. And if you need help, just ask.